Hey everybody, today we are looking at solubility. Now you may be asking, hey, I know solubility. Of course I know solubility. I've seen this before. I know how to use it. Used it many times. Well, there's a little bit more than that, than what you know so far. Yes, you know how to use the solubility table. You can predict if I were to give you a compound like lead nitrate, you will note the fact that, oh, okay, all nitrate will form soluble compound with everything and insoluble with nothing. Oh, okay. Lead nitrate is definitely soluble, right? Remember all of you were able to do that? Knowing how to use the solubility table? Okay. Like another example, sodium chloride. Is it soluble or not? You will note that, oh, okay, yeah, it is soluble. I don't even need to look at this table because I know when I put salt in water, it does dissolve. Well, would it continue to dissolve? Let's say I gave you a whole bucket of salt and I give you a little beaker of water and you were to put salt in, dissolve it. Okay, it dissolves. Put more in, it dissolves. But that may tell you, there will be a point where, oh, you know what? My salt cannot dissolve anymore. Same with things that are insoluble. If I were to give you silver chloride, I'm not going to give you silver chloride. That's pretty dangerous if you think about it. Silver chloride is insoluble. Now, does it mean is totally insoluble? The answer is actually no. The problem with things are, of course, insoluble is that it takes very, very, very little, okay, to precipitate out. Or it can only, or your solvent can only dissolve very, very tiny amount of these things. Okay, so let's get on it. Let's do some quantitative work and see, okay, things are soluble, things are insoluble, like when? So I made a little example here that if you take a look at silver chloride, that is insoluble based on the solubility table. Silver nitrate is soluble, again, based on the solubility table. Oh, one more thing. The solubility table is composed through SATP. Okay? That's one thing that I'm not sure if I told you about. Now, what I just said earlier was exactly what I written down here. AgNO3, this is soluble. Okay? It is only soluble when the solution is still unsaturated. But there will be a point where you can no longer dissolve any more solute. That point, exactly that point, is called saturation point. In this case, this is called saturated solution. All right? Now, every chemical, especially those ones who are not very soluble, has something called a solubility constant known as Ksp. No K. We've seen K before in the form of Kc. That's an equilibrium constant. Ksp is totally related. Okay? Instead of calling it an equilibrium constant for an equilibrium reaction, it is actually the equilibrium constant for a solubility reaction. Okay? Because this is telling you the equilibrium between the solid, which is of course the compound here, along with its ions in solution. Because what we know is that when you drop AgNO3 in water, you get Ag plus and NO3 minus. You don't get AgNO3. But Ksp is saying that this and its respective ions are at an equilibrium. Okay? Now we'll see what that means later. but let me just tell you one more information, that the higher the Ksp is for a certain chemical, the more it can dissolve, or the more of it can be dissolved. So NaCl has a very high Ksp. Hence, you can dissolve lots before it becomes saturated. Got it? Now, same with AgCl. We know that AgCl is not very soluble. What that really means is that only very little of it can dissolve in water. But hey, let's say you have a couple of grains of it, it will dissolve in water. It's not like it won't dissolve. It's not if you have a whole tablespoonful. Now that's a different story. And again, it all depends on how much water you have, right? Okay, so that's the introduction of what Ksp is all about. Okay, it's basically a constant, okay, indicating the equilibrium between the solute, okay, and its respective ion when it's dissolved in water. Okay, now what other information can you pick out of this? Well, before we begin, solubility constant can be at SATP is on chapter 32 in your IB booklet. As you can see, the IB booklet doesn't give you every single chemical there is. It's pretty obvious. They give you enough for you to get by. But if you want more Ksp value for everything, single thing that they tested in this world, go to a CRC handbook, and hey, these are easily accessible. Now remember, these Ksp value are all based on SATP. Okay? And we know for a fact that temperature play an important role in solubility. We know that because we looked at solubility as a chapter before. When temperature increases, solubility increases as well. So let's go back to the salt thing. Okay? You finally figured out, oh, my solution cannot dissolve any more salt. It's totally saturated. But you know what? You decided to put a couple of spoonfuls more. Well, then you heat it up. Okay? You put it on high heat, and you'll notice, my salt continue to dissolve. Well, that's because you raised the temperature. By raising the temperature, solubility of a compound will also increase. But let's say you didn't do that. You kept it at room temperature. And at room temperature, these are the equilibrium constant for your solute. Okay. Now, there's information here that we can uncover. Okay. Such information is, can we convert Ksp into solubility? Okay. Because Ksp, as I said earlier, is usually used for things that have low solubility. Okay, like that lead chloride that I mentioned, the silver chloride that I mentioned. The Ksp value is easily accessible. Okay, because these guys has a very low solubility. Now, things that have a high solubility, a lot of people don't use Ksp. Like for example, NaCl. Okay, you rarely will hear people say, hey, what's the Ksp for NaCl? Because that's going to be a big number. Instead, people use moles per liter. Now, don't mistake this as molarity, okay? Don't mistake this as molarity. What we're saying here with moles per liter is how many moles of NaCl dissolved in 1 liter, okay, in order to reach saturation point. Okay, let me say that again. How many moles of NaCl per 1 liter of solvent, which is water, will it reach saturation point? Will it reach the point where, oh, no more NaCl, can't dissolve anymore? Okay? Or simply by the general public, because not everybody know about mole. You say mole, they think of rats or some sort of rodents, but instead grams per 100 milliliters of solvent. Okay, how many grams of NaCl can dissolve in 100 milliliters of water? Okay, but as a chemist, we want to use Ksp. So can we convert this information into Ksp? The answer, of course, is yes. Okay. Now, I have a question right here. Okay, regarding magnesium fluoride. Okay, magnesium fluoride is soluble. I can tell you this right now. It is actually a soluble salt used to make lenses. Lenses for, I guess, microscope, whatever, okay, something technical. I want you to do one thing. I want you to take this information right here, because this is the solubility point, okay? And I want you to turn that to Ksp. Now, the question is obviously, how am I going to do that? Well, I'm going to show you a little thing, okay? Prove to you a certain, I guess, Ksp value in terms of how that works. And let me just tell you that this means it takes this much MgF2 dissolved in 100 milliliters of water to reach your saturation point. I want this information to be in Ksp. Okay. Now, before we begin, I want to go back here, and I want to prove something. I want to tell you how to write a Ksp expression. So I have, let's say, copper 2 chloride. Okay. Copper 2 chloride dissociate in water as an equilibrium to give you Cu2 plus and 2Cl minus. Okay, obviously these will be aqueous because they are dissolved in water. So if you put copper 2 chloride in water, what you'll find in water is copper 2 plus and chlorine minus, as long as you don't go over the saturation point, right? Well, knowing that, if I were to ask you, hey, what is the Kc for this reaction? Now, a lot of you will say, yeah, that's an easy question, because I know that Kc is equal to product to the power of their coefficient over the reactants and its coefficient. So it would be Cu2, the concentration of Cu2 plus times the concentration of Cl minus to the power of 2 over the concentration of CuCl2. Okay, and you would have been congratulated, and everything will be fine. Now, we're not looking for Kc here. What we're looking for is how to write a Ksp expression, which is a little different. And what a Ksp expression is, okay, is the equilibrium constant as a product with a solute. So what that means is that we might want to move this to the side, because that's what Ksp means. So let me just do that for you. So Kc times CuCl2 is equal to Cu2 plus times Cl minus squared. Okay? To further break this down, this right here is Ksp. Okay? The equilibrium constant times the solute is actually my Ksp value. Ksp is therefore equal to this. That's how you write a Ksp expression for a particular solute. Okay? So, knowing that, I want to know how to calculate the Ksp for MgF2 based on the solubility point that I'm given. So let's do this one together, and then you know what? I always have one for you to do. So if I were to ask you, hey, do this. But first, of course, what is the Ksp expression? Well, we know for a fact that MgF2, okay, dissociate to give you Mg2 plus 2F minus. All right. Let me just put in those states. Really actually doesn't matter much. So what's the Ksp expression? Ksp expression here, okay, is equal to, I might not want to put it here. I might not want to put it because I might want to save this. Ksp expression is Mg2 plus times F minus, okay, squared. That's my Ksp expression for magnesium fluoride. Now, things are usually not abbreviated by grams per milliliters. Okay? Concentration is expressed in moles per liter. The question is, can you turn this into moles per liter? Because that's what I want. The answer, you know. Okay? So let's do that right now. That 0.00172 grams per 100 milliliter, you can easily change that to molarity, because by changing it to molarity, you can find out what these guys are, because that's not hard to find. So let's do that. Let's change milliliters to liter. So for every liter is 1,000 milliliters. So milliliters cancel out. So now you have grams per liter. Now you want to turn grams into moles. And the molar mass for MgF2 is 62.31. Okay. So now you have moles per liter, just like you want it. All right, let me take my calculator and punch this in. That's going to be 2.8 times 10 to the power of -4 moles per liter. Okay, this is obviously something that you have to do, because even though they're giving you the solubility point, but then they give it to you in grams per milliliter. Okay, so you're going to have to somehow change this to moles per liter, because equilibrium expression is based on molarity. Okay, so you now have the molarity of MgF2. Now, this is what you're going to do. You want to find the Ksp expression, right? So most likely at equilibrium. So at equilibrium, this is what's being formed. Okay, so at equilibrium. So what does that mean? What that means is this. I need to find some room here. I'm gonna rewrite this whole thing right here. MgF2, Mg2 plus 2F minus. Okay? What that means is this. At this equilibrium point, at this point right here, that there's no MgF2. MgF2 would have been all dissolved. But if you were to put a little bit more MgF2, there's going to be an excess of this guy. But at this point, as what's being said right here, there's no MgF2. So that will make it quite easy to determine, of course, what Ksp is, because all you need to do right here in this equilibrium is to create a nice table. Okay? So initially, MgF2 dissolves, and they will continue to dissolve up to this point. And they never said anything in this question that this point was further, I guess, put in. So what that means is that for most likely, you're not going to put anything here. Okay? You're not going to put anything there because there's really no point. Because you really haven't seen this unless this is when it went above this, but it didn't. So nothing is going to be incorporated with MgF2 because theoretically this thing gets dissolved. It never started, pretty much. However, initially these guys are not really there. Okay? Now, we know how to do ice table, right? The change is based on the coefficient. So that will be positive x because this is 1. And this will be positive 2x due to the fact that this is 2. Okay? Because as you move along, as this reaction proceeds, you're going to be making more and more and more of these. And how much more is based on the molar ratio. Okay? So for change, you're looking at plus x and plus 2x because these guys started with nothing. They are 0. So I'm going to leave it at that. Okay? Ksp, as I said, is based on equilibrium. Okay? They already have this incorporated into, of course, the expression itself. We know that this is what's given or what's, I don't know, experimentally determined. So all you have to do now is to finish off the question by putting in the equilibrium expression. So that will be x times 2x squared. Okay? Now, what is x? That's the thing. What is x? This is actually x. This has a special name. This is called molar solubility. Okay? This is called molar solubility. It's actually a very important variable. This variable indicates how much, okay, in moles per liter will the saturation point be reached. Basically, this is x. Okay? That is x. So, to make my Ksp expression, I'm going to insert my x into my equation times there we go. Okay, and let me just take out my calculator and it will be 8.4 times 10 to the power of negative 11. So I just turned solubility point, okay, into a Ksp value that scientists publish in, I don't know, any sort of constant literature, okay, and really there to prove that Ksp is derived, of course, from equilibrium constant, because you're at equilibrium, these guys are all equal. Okay, we don't care about the MgF2 because, first of all, it's negligible, okay, to even know, because Ksp actually take care of whatever this is, and assuming that they start out at 0, and they usually are, and if you were to just create the equilibrium expression as is, and plug this, of course, into your Ksp expression, and knowing the fact that this value right here is experimentally determined, and you turn it into a molarity, that has a special meaning known as molar solubility. Okay, so put that all into your expression, and you should get, of course, your Ksp value for that particular compound. So hopefully that's not too hard to do. And again, I do have one for you to do. Okay, so for the Ksp of zinc hydroxide, okay, you can easily find it in your IB handbook. Okay, so let's do this one together. Okay, now this one I'm not asking you to find Ksp. This one I'm asking you to find molar solubility. Okay, so if you remember, this is molar solubility. So I'm looking for X. All right. So the only thing missing here, of course, that if you're asking me for molar solubility, which is really the reverse of this question, where's my Ksp? Can I find Ksp? Because I do just say SATP. So of course, okay, let's find out what that is. Ksp for zinc hydroxide, right here, is, there it is. Okay, 3.0 times 10 to the power of negative 17. Let me just look at this one more time. Yeah, there you go. Okay, so that's the Ksp value for zinc hydroxide. So this time I want to look for molar solubility. I want to know what is the saturation point where I can't dissolve this anymore. Okay, so hey, let's do this. So we know that zinc hydroxide dissociate to give you zinc 2 plus and 2 hydroxide ion. All right, and let's do a nice table. We know that this is negligible. Okay, let's say we start this at 0, and we're making more and more of these. Okay, so at equilibrium, zinc is going to be actually the molar solubility, and hydroxide will be 2 times of that. Okay, so knowing how to make a Ksp expression, so the Ksp is equal to zinc 2 plus times OH minus squared. Okay, and by looking at the constant booklet, we already know what Ksp is. We know zinc is represented by X, which we want to find, and OH is represented by 2X. All right, so hey, there you go. They're asking you to find molar solubility. Find X. Okay. All right. Oh my goodness. Is this going to lead me to a cube root? I don't like cube root. 4x squared 3. Yeah, this is going to lead me to a cube root. My goodness. Okay, so x is equal to the cube root of 3.0 times 10 to the power 17 over 4. X is therefore equal to, this is going to take me a long time because I'm not sure if I know how to do cube root in my head. All right. No, that's not right. Four. The answer is 1.96 times 10 to the power of negative 6 moles per liter. Okay, there it is. That's the answer right there for the molar solubility of zinc hydroxide at STP. So what that means is that it takes 1.96 times 10 to the power of negative 6 moles per 1 liter of solvent to reach saturation point. Okay, so if you want to know what that is in grams, feel free to multiply this number by the molar mass of zinc hydroxide, and you know how many grams of zinc hydroxide you need to for it to no longer dissolve in 1 liter of water. Okay, so hopefully you are comfortable with the language of Ksp, okay, and molar solubility, and be able to kind of convert these two based on what we did in the first two examples. Right? Now, those are not very important. What's important is predicting precipitate. And again, you're probably saying, oh yeah, I know how to do that. I've been doing that ever since like grade 10, remember? I usually don't say things like that, but if I give you this reaction right here, and I ask you, it's this reaction to give you products, and you will, of course, know, oh, okay, this looks like a double displacement reaction. You're going to get NaCl, and you're going to get CaSO4. Okay? And by looking at this, definitely am I going to get a reaction, because we know that CaSO4 is a precipitate. Okay? Now the question is this. What happens if you're given very, very, very little amount of this? And you're given a lot of these. Lots. Less. So a very, very little of calcium chloride. A lot of sodium sulfate. Are you still going to get precipitate? Now, if you remember what we said earlier here, okay, about Ksp, that things are soluble up to a certain point. Also, things are insoluble also to a point. Meaning that if you're given very, very low concentration of this, or very, very low amount of this, but lots of solvent, you may be able to dissolve a little bit of AgCl. Let's go back here. If you're given very little of, let's say, this, but there's a lot of this, there will be this reaction may not happen, because you may not reach that saturation point and beyond to create calcium sulfate. So in reality, when you're trying to do this experiment, you may tell your teacher that this reaction has no reaction because I don't see a change of color, I don't see no precipitate. Yeah, but then you may be wrong, because it's supposed to form a precipitate. It's just that the amount that you used to begin with did not reach the Ksp point. Now, how do I know if I reach my Ksp point? Well, we're going to have to find this guy. We looked at it before when we looked at equilibrium constant again. We looked at this in the form of Qc to see which way does the equilibrium favor. Okay, towards product or towards reactant. We're going to do the same here. Okay, we're going to find Q. But this time it's based on will precipitate be formed. Because if you calculate Q and Q is greater than Ksp, oh yeah, precipitate form. Meaning that you have enough of this and you have enough of this to make this work. But however, if Q is either equal to Ksp or less than Ksp, you're going to think that this reaction will not proceed. You're going to think that this guy won't be made because precipitate is not going to be there because you haven't reached that saturation point and beyond yet, or beyond the saturation point, because as you can see, even though if you are at saturation point, you still get, you won't get this. Okay, you're still going to be out of this. You have to go over in order to see the precipitation. All right, I have a question right here. Okay, so you're reacting calcium chloride with sodium sulfate. Okay, and let me make sure that this is balanced. And what you're going to get is 2 moles of sodium chloride and a mole of calcium sulfate. I want to know if this will actually form. I want to know if this have reached Ksp point. Because if it hasn't, if Q is less than Ksp, as we mentioned here, no precipitate. But if Q is greater than Ksp, that means, hey, you have enough of this, you had enough of that to make this happen. And the Ksp at this time, 20 degrees Celsius, which I'm going to give you, is 3.6 times 10 to the power negative 5. So determine if PPT will form. All right, so let's do this. Basically, CaSO4, okay, dissociate to give you Ca2 plus and SO4 2 minus. Okay, that means that Ksp is equal to calcium 2 plus times sulfate 2 minus. Oh, thank goodness. Thank goodness there's no coefficient here. So that way there's no exponent here that will really mess up my math. All right, so let's find Q. Now, to find Q, you need to change Ksp to Q, because later on you're gonna compare whatever this is to that to determine if PPT will form. Now, what we want to do is to find out what this is and find out what this is and multiply the two numbers together. Now, that's not hard to do. Just a lot of stoichiometry, a lot of calculations. So let me do this using color. So let's say I'm gonna look at this in blue. I'm gonna look at this in orange. I hardly use orange. Okay, so let's take a look at calcium. How do we find the concentration of calcium 2 plus? Okay, now that's pretty simple. We know that 0.1 mole of calcium chloride is in a volume of 0.1 liters. Okay, this and this cancel, and what you're left with, of course, is 0.01 moles. Well, not what you're left with. This has 0.01 mole of calcium chloride. Okay, and since calcium chloride and calcium is 1:1, since CaCl2 and Ca2 plus is 1:1, Ca2 plus is equal to 0.01 mole. Now, we're not done here, because what is the molarity of Ca2 plus? Because right now, we know for a fact that you're dissolving 100 milliliters of this to another 100 milliliters of this. So in total, in terms of volume, there's actually 0.2 liters. Okay? So calcium's concentration is actually 0.05 molar. Okay, we got half of it done. Now let's look at the orange. So let's do SO4. Okay, so we have 0.04 moles per liter. How many mole is that? Well, that's 0.1 liter, so therefore the amount of mole is 0.04. I don't know why I need my calculator for this, but that will be 0.004 moles. Okay, now Na2SO4 to SO4 is also 1 to 1. So what that means is that SO4 is equal to 0.004 moles. Okay, so we're going to do the same thing. SO4 2 minus is 0.004 moles divided by total volume, so that's 0.1 liter plus 0.1 liter. Okay, so that will be 0.02 mole. So I have my SO4. I have my Ca2 plus. So all I have to do right now is to plug that in here, plug that in here. Okay, because I got the concentration of both entity after it mixed. Now I want to check what my answer is. So let's go back to red. So Q is equal to 0.05 times 0.02. I'm glad there's no exponent. Okay, and the answer here is let me put this in scientific notation. 1.0 times 10 to the power of negative 3. Okay, that's my Q value. And now I'm going to compare it with Ksp. And I notice here in conclusion that, Q is actually greater than Ksp. Okay, what I've put in here is actually more than enough to satisfy saturation point, which is quite low if you think about it. Therefore, PPT will form. Okay? That's how you determine if you'll see precipitate or not, is to find out what is the concentration of calcium based on what you got and what happened after you dissolve, so the final concentration of this, and taking a look at the same thing for the other ion. Okay, in this case it would be sulfate. Okay, find out how many moles of sulfate there are and divide it by the total volume. Multiply the two numbers of the equilibrium expression. Make sure they're right. Okay, and whatever Q value you got, compare with your Ksp. If Q is greater, that means, hey, you know what? The amount of these two guys have already went over the saturation point. Of course you're going to get precipitate. But if Q equals to Ksp, or Q is less than Ksp, that means you haven't reached saturation point yet. You might need more of these or more of these to make that happen, because one participant here is just not enough to give you that number or beyond. Okay. Whew. It's a little messy. I should have allocated more room to do this, but I think you guys can allocate some room yourself, right? So I want you to do this question. I can tell you right now the answer. The answer is no. As in no PPT. No precipitate. Whatever you're given here is definitely not enough. That's why they made these such small numbers. So I know for a fact that, yep, that's right. Now you may be thinking, all right, this is a big question because I'm going to have to find out what the product is, find out which one is the precipitate, and then do all the math to determine if the precipitate would occur. Okay, by comparing it to QC. But oh gosh, nobody give me Ksp. Well, let me just start this off for you. This is going to give you sodium sulfate, 2 of them. And then it's going to also give you lead sulfate. Okay? Is lead 2 sulfate a precipitate? I can tell you right now it is. So no need to look at the solubility table to determine. Okay? Because it is. But you need to look at this. Okay? You need this number. Because you're going to compare your Q with this number to determine if you're going to get PPT or not. And I'm going to tell you right now that your answer is no. And all you have to do is just do the math like I did in the question earlier and determine that factor. All right? So this is obviously something very different, very new, very fresh, and very useful. And not sure why I didn't put that into your curriculum, because I believe this is useful stuff, just useful in the long run in the realm of chemistry. All right, one more topic and then we're done. Okay, it's called common ion effect. So let's say you have a solution right here. Okay, you have a solution of NaCl in water. So you're going to get a whole bunch of Na plus and Cl minus. A whole bunch of Na plus and Cl minus. Whole bunch of Na plus and Cl minus. Okay? And for some reason, some guy decided that it's a good idea to put in some HCl in there. Okay. What happened when you put an acid in a solution? That's right. You get dissociation. Oh my gosh. Take a look at this. Now you have an over-influx of chlorine ion. Look how much chlorine ion there are. Okay, too many. That's why we call this the common ion effect. Now, what will happen here? Okay, is it just for the fact that, oh, there's a lot of chlorine ion and it's going to be acidic? No, no. There's more than that. If you decide to put a lot of this in here, what might happen is these guys will say, oh my gosh, that's a lot of chlorine. Get back together. Get back together. Let's precipitate. Now, think about it. NaCl forming a precipitate? Never heard of, right? Because NaCl is totally soluble. But hey, in the realm of common ion effect, that might happen. Why? Because NaCl, okay, dissociating to give you Na plus and Cl minus can be reversible. When would it go this way is my question, because usually it goes this way. Unless you have too much of this. If you have too much of this, you just won't go this way anymore. It will just be, I'm just going to stay here. I'm not going to go this way. But very rarely would these guys will say, hey, let's get back together and go back. Very, very rare. Unless you decided to add more of these. Take this guy. Let's add more of these. Let's purposely raise the concentration of this number. Now remember, for every equilibrium, there is a Kc. Okay? When you have an excess of product, obviously right now your Qc will be far greater than your Kc. What happened when your Qc is farther than your Kc? That's right, Le Chatelier principle. He said when this happens because you have too much of this, so when you multiply this number and this number together, this number is bigger than your Kc. Well, guess what? I'm going to go back. And that is what happening to this situation. Before, it was nice and fine. NaCl dissociate, you're going forward. But some dude decided that it was a good idea to put more Cl in there in the form of HCl, causing too much of this. So when you multiply this and this together, oh no, it went greater than what Kc is. I'm going to have to go back. What that means is that NaCl will precipitate. Okay? Because of an excess of Cl minus. Okay? So that's what common ion effect will do to your equilibrium. Okay, so if you have some salt water in here and you want to get the salt crystal back, it's very simple. Put some acid in there, but only hydrochloric acid though. Okay, you can put sulfuric acid in there, nothing's going to happen. But if you put hydrochloric acid in there, you'll notice that salt crystals start to form at the bottom of this beaker. Okay, all right. I have one final question. I want to find out the molar solubility. Do you remember what he was? That's X. Okay? The solubility point of PbCl2. So what is the solubility point? Okay? In moles per liter of PbCl2. If I have this amount of sodium chloride at SATP. Now I noticed that in your IB booklet, PbCl2 Ksp is not given, so I'm just going to give it to you right here, and let's do this question. Okay, let's see how we're going to tackle this question. So we want to know what is the molar solubility of PbCl2. So let's write the expression. PbCl2, okay, is Pb2 plus Cl minus, at least two of them, in a nice table where this is negligible. These start out as nothing. Okay? And for the change, this is positive. You're going to get more of these by 1 molar, and you're going to get 2 of these by 1 molar. And we want to find what X is. Okay? X and 2X. Now, that's what it would have been without this mess. But no. You decided to put 0.2 molar of NaCl in here. Now the game has changed. What has changed? Initial has changed. Because right now we have a common ion effect. Because what you did is that you inserted NaCl into the system, which means you did not start out with 0 here, didn't you? No, you didn't. NaCl dissociate to give you Na plus and Cl minus. Cl and Na is in a ratio of 1 to 1. So if this is 0.2 molar, this is 0.2 molar. What that means is this is not going to be 0. This is going to be 0.2. Okay, so common ion effect had actually give you something for one of the product to start right off the bat. Okay. Now, that means this is going to be more than 2x. This is going to be 0.2 plus 2x. The initial plus the change. All right. Now you can find x, because my whole idea here is to really find out what this is. And again, it's going to be Ksp is equal to Pb 2 plus times Cl minus to the power of 2. So that's 1.7 times 10 to the power of -5. An ugly looking -5 is equal to x times 0.2 plus 2x squared. Okay. I will tell you this right now. You're going to run into a huge mathematical problem. This is a huge mathematical problem. When you combine all of this mathematically in a polynomial, you're going to get some sort of cube root. Okay, it's going to be a mess to find what x is. Do you remember there's a way to say if x was a very, 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 very small number, you can ignore certain things? Remember something stupid like that? That's right. Let's take a look at here. Can we say 0.2 plus 2x is kind of just equal to 0.2 because x is such a small number? We don't know if x is going to be a small number, but we can test to see if it's a very small number. And yes, if you're wondering in your head, oh, Mr. Lung is probably thinking about the 100 rule. Yes, I am thinking about the 100 rule. I'm going to apply 100 rule to this, because I want to know if this is going to be a very tiny number where I can just say, ignore you, because you are giving me a big problem. All right, let's see if you remember. The 100 rule is very simple. You take the initial concentration, okay, and you divide that by the Ksp. Okay? Initial concentration divided by Ksp. And let me just put that down into my calculator. And you should get, oh, something that I usually see in my bank account. Oh, no. That's only 11,000. That's not my bank account. I have more than that. Okay, let's not just write this down, because that's really negligible to write what that is. It's not really useful for you guys, but I'm going to say it's greater than 100. Okay, this right here is greater than 100, so therefore 0.2 plus 2x is equivalent to just 0.2. Okay, what a good review, because I'm not sure if you guys remember that. So let's go back here now. Is equal to x times 0.2 squared. Okay, because 0.2 plus 2x is really just 0.2. Guess what? I'm just going to skip everything because I kind of know the answer to be 4.2 times 10 to the power of -4. Okay? So that is the molar solubility of PbCl2 under the influence of NaCl. So what this number means is that to reach saturation point, okay, this molarity, or you can say 4.2 times 10 to the power of negative 4 moles per every 1 liter of of water will give you a saturation point. Anything more than that, you will start to get a precipitate. Okay? So that's common ion effect. Obviously, without this number would have been higher. Okay? Your water would have been able to take more of these. But nope, you start off with something because somebody decided to put in some outside factor in. So that will actually decrease your solubility of whatever you had earlier. Okay? All right. That's it. Okay? In terms of solubility, I hope you guys sort of understand exactly how it works. As I said, this is actually very important stuff. It's real physical chemistry. And the next time, or actually tomorrow, we will look at strong acid and strong base titration curve. Now, we did titration, okay, in a sense of looking for the unknown acid concentration or the unknown base concentration. We even did it, okay, back in December. But what I want to do with you guys tomorrow is to actually graph out these kind of things. Okay, how do we graph a titration curve? If I were to add a little bit of base into my already existing acid, how would the pH change? Okay. All right, so we'll do that tomorrow. All right, so have a good day, guys. Bye.